Hello everyone, I'm Ghada Sokar and I will present our paper Dynamic Sparse Training for Deep Reinforcement Learning. This is a joint work with Elena Mekano, Dashabel Mekano, Mikola Personiski and Peter Stone. So first of all, what's Dynamic Sparse Training? Instead of training a dense neural network, in this line of research we aim to train a sparse neural network from scratch. And during training, we optimize both the weights and the sparse topology. The sparse topology is optimized through drop and grow phases, where we drop a percentage of the least important connections in each layer and regrow the same percentage in different location in each layer. And we keep performing these drop and grow cycles during the whole course of training. And this is different from static sparse neural network, in which we randomly initialize the network with a sparse topology, and this topology is kept fixed during training. So this line of research has been started in 2018 by Dashabel Mekano and his co-authors by proposing the set algorithm. After that, many interesting works appear in this direction, aiming to improve the performance of sparse training. And as you can see here in the reported results by one of the recent papers, with very high sparse model, with only 5% of the connection or 2% of the connection, we can achieve a very comparable result to the dense model. So most of this effort are devoted for the supervised learning, in particular for image classification tests. So the question is, can the same observation be valid in the deep reinforcement learning paradigm? And that's what we study in our paper. So what's the difference in deep reinforcement learning? The main difference is that there is no label data, and the policy is learned through many cycles of trial and error, and the data is collected while the agent interacting with the environment and improving its policy. So this leads to two main challenges. First, the agent faces distribution shift during training. Second, it requires a very long training time to obtain a good performance, and this is mainly due to the many interaction and trial and error cycles with the environment. And for sure, the computational cost would be a factor of the neural network size. So in our paper, we introduce dynamic sparse training for deep reinforcement learning. In particular, we apply our proposed method to two actocritic methods, TD3 and SEC. Here I will give a quick overview of our modification to the TD3 method, and you can find the full details along with the SEC method in our paper. So here is a schematic view of the TD3 method with our modifications highlighted in blue. So the first thing is to use a sparse network instead of a dense network for the actor and the critic networks. So at the beginning, we initialize this network with the random sparse topology. And then our second contribution is our proposed adaptation schedule. So typically in supervised learning, the adaptation process of the topology is performed every training epoch. However, we find that in the deep reinforcement learning paradigm, it is very necessary to delay this adaptation process and decrease its frequency so as to give the connection added from the previous adaptation process time to grow and learn in this online setting. And according to our adaptation schedule, we update the topology of the actor and critic. And here we use the criteria from the set algorithm to drop and grow the connection. So we drop a percentage of the connection with the least magnitude and randomly grow the same percentage. Finally, we add a module to maintain the sparsity in the target networks. So typically in axiomatic methods, the target networks are softly updated by the current networks, and that could increase the density level of the target networks. So we, after each target update, we maintain the sparsity level in the target networks by pruning the extra weights based on their magnitude. So let's look at some experiments and results. So we performed our experiments on continual control tests and tests on 5 environments. Our baseline are the original TD3 method with a dense network. And also we add another baseline, which we call the static TD3, in which we initialize the model with a sparse neural network. And this topology kept fixed during training, and our proposed DSTD3. So here is learning curves on 5 environments. As you can see, the blue curve is the STD3, and the original TD3 donated here in blue, while static TD3 presented in green. And in all cases, we observe that the STD3 has a higher final performance than the dense one. And more interestingly, we observe that it has a much higher learning speed. With only 50% of the training steps, we can achieve the same performance achieved by the dense one after performing the full training steps by the dense one. So this is very interesting because it will decrease the number of interaction with the environment by 50%. For the static TD3, we observe that it could achieve the same performance of dense TD3, which is also very interesting because it will reduce the memory and computational cost. However, it doesn't have this higher speed advantage of the dynamic sparse model. Here is a quick video on a humanoid dataset. After performing 400K of the training steps. So as you can see, the STD3 starts to be stable. However, STD3 keeps falling. Okay. Then we analyze the effect of the adaptation schedule in the final performance and the learning speed. So we test a very frequent update of the sparse topology using E200 and E500. And we also analyze a very low frequency of update where we use E of 2000. And our used setting in the paper where we use E of 1000 steps. So as you can see here, a very frequent update of the topology doesn't achieve the same higher speed as a moderate update. And this is due to this fast update could give unbiased estimate of the connections that have been just added in the previous topology update. And also a very low frequency update will hinder the exploration of different sparse topology and slower adaptability to this changing distribution. This obtained results was with 50% sparsity, which consequently reduced the computational costs represented here in flops and network size by 50% while achieving a higher performance than the dense one. Finally, we analyze the effect of the sparsity level in the learning speed and performance, and we find that with the 25% sparsity or 50% sparsity, we can beat the dense model with a higher learning speed. But when we evaluated a higher sparsity level, like 80% in this case, it fails to achieve the same performance of dense model. And this is one of the challenges and still open questions in the reinforcement learning. As I showed you at the beginning, in the supervised setting, now we can achieve a very comparable performance using 90% or higher sparsity, but it's still very challenging in the reinforcement learning setting. So, conclusion, in this paper, we introduce dynamic sparse training in deep reinforcement learning, and we show that it has many advantages. First, it reduces the memory and computational costs, reduce the interaction with the environments and the training steps, which means that we could increase the sample efficiency. It has a faster adaptability to the change of distribution in the reinforcement learning paradigm. And finally, we could achieve a higher performance than the dense model. So possible interesting future direction. It would be very interesting to obtain a new method that could achieve a higher sparsity level for this paradigm. And in this work, we evaluated the set algorithm as a dynamic sparse training. Could also be interesting to evaluate other dynamic sparse training method or propose a new one specifically for this paradigm. And we saw the effect of the adaptation schedule. So dynamic or automatic adaptation schedule also be a very interesting direction. Thank you for your attention, and please feel free to reach out if you have any questions. Thank you.